Check, check, check. Good afternoon, everyone. Am I audible and
Good
now visible
afternoon.
also?
Good afternoon, sir.
Good afternoon. So I've changed the video background a little. So today we will start something new. We will be getting into the unit of correlation and regression. Regression we will discuss later. First, we will discuss correlation. Okay. And before that, actually the concept of correlation becomes much simpler if we also include covariance. If we start with covariance, then it is very easy to understand what is correlation. So I'll share my screen. So there's a very nice thought. Till I open whiteboard, you can quickly read it. Okay. So we'll be starting with covariance. Yeah. So we fortunately have come across the term variance. Variance already we have come across. Yeah. So when there is only one variable, say the temperature at a place, 20, 21, 5, 19, 18, like this. This is temperature in degrees Celsius. So as a measure of dispersion, as a measure of how much the data is varying, we calculate the variance, and from there we calculate the standard deviation. So how do we calculate variance? First we calculate the mean. Mean we calculate, suppose let's call it x bar only. Yeah. So from mean, how each data is different, how far each data is. So that we calculate for each data. Then we sum those differences and take an average of those differences. Actually, we square these differences and then take an average of those of some of those squares. So this is variance. Now it's only one variable. Now many times we would be interested in how two variables vary together, like temperature and number of buses running in Pune. Yeah. So it would be, I'm just taking figures. Maybe it is little too high. Let's keep it in 700, 800. So 750, 500, say 600, 600. So we can try to find out how these two variables vary together. This concept is very important to understand. In covariance, we are trying to find out how two variables vary together. उसका एक measure we are trying to find. We are trying to measure. We are trying to find a way to have a number to express the extent to which variables vary together. Please be clear about the fact that this varying together does not mean that one is causing the other. Yeah. We have no proof that one variable is causing the other. Whether temperature is causing less buses to run, or somehow less buses running is causing the temperature to go up. Nothing like that. That is, causation is not implied by what we are doing here. You cannot say that one variable is causing or is the reason of the other variable. We are just trying to measure whether they are varying together. दो वेरिएबल एक साथ वैरी कर रहे हैं या नहीं, वो हम फाइंड आउट करने की कोशिश कर रहे हैं. इसका मतलब ये नहीं है कि एक वेरिएबल दूसरे वेरिएबल का कारण है या एक वेरिएबल से दूसरा वेरिएबल हो रहा है. ऐसा बिल्कुल नहीं बता रहा है स्टैटिस्टिक्स. बाद में with further studies, further study of the phenomena, further study, more detailed study, we may be able to find out that one variable is actually causing the other. But what we are doing here is just a measure that two variables are varying together or not, trying to find that. Now we have two variables. Now covariance will be so here for this variable we will have a mean, say C, x bar C degree Celsius or x bar B buses, mean number of buses. Here also we will have a mean and here also we will have a mean. So now covariance, we will try to multiply the difference of each number from its mean. How? Let me explain. This 20 minus x bar C, this x bar 20 minus its mean. We will multiply it with 750 its mean, x bar B. So this will be one product. Then we will take the next set of products, 21 minus again its mean, this mean, multiplied by 500, that is the other variable, next point in the other variable, how far it is from its mean, the other variable's mean, that is x bar B. So like that we will write all the numbers. We can also have a notation like this summation, which makes things very easy. The notation also means that we are adding all these numbers. We will see the notation also. So how will be the next number, next pair of numbers? 25 minus x bar C. Actually, you can find out x bar C. All the numbers are given. So it will be probably an exercise. So 500 minus its mean. Only two pairs left. 90 minus x bar C, that is its mean, and 600 minus its mean. That's 80 minus x bar C, the last pair, and 650 minus x bar B. So this shows, this gives an idea of how these variables differ from their respective means, okay, and how they are varying together. So this sum, get a even better estimate, we take the average, that is we divide this thing by n. N here is 1, 2, 3, 5. So n here is 5. In this case, it is 5. in terms of notation, if we want to write this, in terms of notations, if we want to write this, this is, say, let me call it temperature in buses. So PI, yeah, each of this is PI. Each of these temperatures are 1 PI. So this is T1, 20 is T1, 21 is T2, 25 is T3, 19 is P4, like that, 18 is P5. And we will call these P1, P2, P3, P4, and P4. These buses numbers. So this will be P1. In terms of rotation, we can write Ti summation of Ti minus it's the there being temperatures multiplied by D. Each of these numbers taken one at a time. That data is number of buses summation divided by n. This is temperature and buses. We write like this: two variables, one variable, comma, second variable. So now compare this formula for variables. Keep screen. Okay. Sorry. By the way, you have a look at this. It says when only one variable is there, so we are taking the difference from the mean and we are squaring it. So another way of writing this would be summation xi minus x bar multiplied by the same thing, square divided by n. So when there are two variables, what we are doing is we are taking the difference from their respective means. Okay. Now coming back to the formula for covariance, here we are taking the difference from their respective means. Rather than squaring, like in variance, we are taking the difference from their respective means and multiplying and then taking the average, that is divided by n. So this is the covariance. So what it does is it at least tells that whether they are varying in the same direction. These two variables, temperatures and buses, are varying in the same direction or opposite direction. That is whether they are in direct proportion or inverse proportion. When one is increasing, whether the other is increasing, that is directly proportional, or when one increases, the other decreases, that is inversely proportional. That much it tells. Yeah. The sign itself will tell. So covariance can be negative and positive. So the sign will tell whether they are varying in the same direction together, or when one is increasing, other is decreasing, like that. That much will be clear from covariance. Now, as you can see, the units of these two are very, very different. Even the magnitude can be very different. So this is in 20s, 30s, this is in hundreds. So these are all in tens, these are in hundreds. cases, the other variable, the difference in these units could be even larger. One could be in tens, one could be in 10,000s. Then in that case, just taking the product of those differences do not give us a fair picture of their relationship, the strength of their relationship. The strength of their relationship is not clear from covariance. And covariance can be anything. We cannot compare two covariances. All it does is tells us whether the given two variables are varying in the same direction or in the opposite direction. Yeah. It doesn't give us the strength of that relationship. So we cannot compare also two pairs of variables and two different pairs of variables. How strong or how weak the relationships are between these pairs, we cannot tell by covariance. So what we do is, we, in a way, in statistical terms, we normalize this. That is, we divide this thing by the standard deviation of each of these variables. Each of these variables. So to take care of scales, take care of different scales. In which two variables are measured, two given variables are measured, two variables in which we are interested in finding the relationship. Standardize the covariance. That is, we divide the covariance by the standard deviations of the variables. Now we know that standard deviation is a more robust measure. It is, for one thing, it is in the units of the variable. It's in the units of the variable. Here, the units is square of, yeah, standard deviation becomes in the units of the variable standard deviation, and this will have a very different unit. So when we divide by the standard deviations, the result will be unitless. So here, if we try to find out the units for this, it will be degree Celsius. For this term, it will be degree Celsius multiplied by the number of buses, that is, okay, in this case it is unitless. So number of buses, that is unitless, divided by n. Suppose degree Celsius and say distance. So it would have been degree Celsius and centimeter. So it has no meaning. But if we divide this by its standard deviation of the respective variables. So standard deviation of this will again be degree Celsius in degree Celsius, and standard deviation of this variable, suppose it is some kind of a distance, just for example, so again it will be centimeter. So this will be, so this resultant will be dimensionless. And dividing by the standard deviation takes care of different scales. Whatever may be the scales, we are dividing that value by the standard deviation. That is, we are standardizing it. Yeah. So what happens is, when we write in terms of notations here, So to take care of different scales in which given variables are measured different scales, we divide the covariance by standard deviations of the variables and get the correlation. That is why we need correlation to take care of two variables being in different scales, which is very much possible. So correlation would be write as R. This this widely used correlation is also Pearson's correlation coefficient. Covariance. Let's sometimes write just COV. Even COVAR may not be written. So just COV is also a symbol for covariance. Covariance. Continuing with the same example, covariance between P and P divided by standard deviation of P and standard deviation of P. So this will be a dimensionless property, and fortunately we get a value between -1 and 1. Covariance can be anything, anywhere, but correlation, not only it has all these positive points, yeah, the reason to get correlation, we also get a value between -1 to 1. So now we can compare correlation between two sets of variables, say temperature and distance, and correlation between another two set of variables, say temperature and rainfall in centimeters. So we can compare the strength of relationships between two pairs of variables using correlation. Then we use correlation to find something else also. Actually, when we try to discuss, when we use different statistical methods like factor analysis and other such methods, other such very nice methods. So we are not directly dealing with data. First, we have say one set of variables, and we find out first correlations between each of pairs of those variables. Then the further all processes are based on the correlation matrix. Yeah, we almost forget about the original data. From the original data of different variables, we first calculate the correlation matrix. Then all the further processes in methods like factor analysis and other such methods, other advanced methods, even advanced than factor analysis, we work with the correlation matrix. That is how important correlation is, the concept of correlation is. And it will also help us in finding out, it will also help us in regression. It will also help us in the concept. This all about correlation, how we can derive this concept of covariance, and why do we need this? Is this clear? Tell this is clear. Check. Am I audible? Am I still connected?
Yes, sir, you're audible.
Audible? Okay. So, how about correlation? You see, are you able to realize its importance? We will soon do a problem. Shall we do a problem? I selected a few. So basically, you can see this will become formula correlation. Maybe it makes sense to write that also. So covariance formula, say x and y. Say this is x and this is y. So this would be. Shall I convert it to x and y, or are you comfortable with t and p also? Okay, let's do both. Yeah, keeping t and p. So this covariance will be summation of di minus mean of that divided by number of buses di minus mean of that, which was xd, I think. Yeah, x bar p. Divided by, it will be summation of pi minus. So this divided by n, of course. This divided by n. So the numerator is covariance. Yeah, that is what we did in covariance. Yeah, this divided by n. Divided by some standard deviation of this. This gives the variance and this gives the standard deviation. X bar p, square of that, summation of all those differences, average of those, average of that, and square. So in terms of x and y, if we call temperature as x and distance or number of persons as y, so this formula can also be written as xi minus y. Because in most of the literature you will find something like this, so you should not square root of xi minus x bar whole square summation of that by n and yi minus y square of that differences. This is clear. This step is clear. Something in chat. Okay, what is T and B in the formula? T is the temperature. T is the temperature and B is the number of buses. This original data we are, this initial example we are continuing with. So these are all number of buses. And these are all temperatures. So these are all temperatures. Okay. Correlation is covariance divided by the standard deviation of each of the variables. And if we the original formula for covariance and standard deviation, we get an expression like this. And here, is this clear till now? Can anybody say how we can simplify this a little bit? Take a moment, take a minute, and try to see how we can simplify this expression a little bit. Take 1 minute. Square roots will become no, square roots will not get cancelled out. These are two different, very different expressions inside this equation. It's not that one xi minus x bar will cancel out this xi minus x bar somehow, because you're not just leaving those as products, you're summing them up. You're summing up all these differences. So when you expand, you will cancel out these things. But still, we can simplify this a little bit, not that much, but we can simplify it a little bit. Yes. Check. Check. Yeah. The indicator is showing I am audible. So I hope I am audible. So any ideas? See this n. Yeah. In the numerator, there is a n divided by n. And these n's are actually under the square root sign. So each of these is square root of n and square root of n. And above there is an n. So if we have this entire thing, so basically this becomes xi minus x bar minus y bar summation of that divided by n. Divided by, I am writing divided by, it is same as writing below this, divided by summation of psi minus x bar whole square divided by square root of n. Yeah. So square root of this whole thing, we can separate square root of numerator, square root of denominator, multiplied by square root of summation yi minus y bar whole square divided by square root of n. So this square root of n and the square root of n we can combine. It becomes n. And this is division, right? This is division. So division means multiplication with the reciprocal of the number. Okay. Dividing by the number is same as multiplication by the reciprocal of the number. So 8 divided by 4 is same as 8 multiplied by 1 by 4. Okay. So the same thing applies here. So this is xi minus x bar y minus 4 bar by n multiplied by n into root over n, or we can combine these two root over n and just write n. Okay. And in the denominator it will be summation of xi minus x bar whole square square root of summation of yi minus y bar. So this n basically gets cancelled out. This is the simplification we can do here. So the ultimate formula, I mean the final formula in terms of xi, very granular formula. Divided by summation of xi minus x bar So basically this formula, this is also R correlation coefficient R, this formula. In terms of concise notation, this formula. It's basically same. This is much easier to remember. Two variants of two variables divided by standard deviation of each of those variables. In words also, if you remember, it will make it much easier to remember this formula. Correlation equal to two variants of the two variables divided by standard deviation of each of those variables. That if we put the granular formula, if we put in place of each of these terms, ultimately we get something like this. Of course, while calculating, it will be easier to use this. Remember, it will be easier to use the other formula, this one, and while actually calculating, especially while calculating by hand, this will help. So now let's have that problem. Let's see. Yeah. Pearson's coefficient is the correlation coefficient we calculated. Yeah. So that is also called Pearson's correlation coefficient rather than just correlation coefficient. There are a couple of other types of little more complicated correlation coefficients, which are rarely used. Pearson's correlation is the most widely used correlation coefficient. Generally, correlation means Pearson's correlation coefficient, which we just discussed. Okay. So now this is the problem. A little bit of a solution. Solution can also you can see. So to try not to see that. Yeah. So let's focus on this part. Compute Pearson's coefficient of correlation between advertisement cost and sales as per the data given below. Yeah. Advertisement cost in thousands, 39,000, 65,000 is given, and sales in lakhs, 47 lakhs, 53 lakhs, and so on. It is given. So could you be able to calculate the correlation coefficient? You can take this data If you need more practice, I'll pass on such problems. I have two sets of such problems. Two sets, yeah, not just two problems, two sets of such problems. You can practice as much as you like. One or two problems definitely we are taking up in class. This is the first problem. So, how much time would you need? 3 minutes, 4 minutes? Yes. Harish, Kartiki, Pradeep, how much time do you need? Okay, somebody has written. 4 minutes. Okay, 4 minutes. Done. So I'll mute myself. 4 minutes. I'll project. Just take this down or take a screenshot and save it as Word document. At the institute, there has been at least one positive case, so we are taking precautions. It's good that right now you're not visiting the campus. Yes, so I hope you have noted down these data, these sets of data, 3 plus 3, 6, 9, 10 data points for each of the variables. Now find the correlation between these two variables. Again, let me repeat, we are finding correlation. We are trying to find out how these data are varying together. But that in no way means that one is causing the other. For causality, we have to go much deeper into the context, into that situation, that particular situation. But with the help of statistics, we can at least find out if the two variables are varying together. If there is no correlation at all, yeah, if correlation is 0, then what's the point in going deeper? So at least to decide whether to go deeper or not, we will be first checking the correlation. So that is the utility of this concept. Yeah, I'll check formula.
So you're still sharing the screen.
I think there was some confusion on today's timetable, but I had checked in the morning. Maybe there were some changes. Okay. Yes. Yeah. So if anybody is left out, you put the message in the group itself, because if not me, somebody else will notice and tell. Yeah, somebody who is already in the meeting will notice and put it in chat here, which will be much easier for me to notice and everybody to notice and take some steps. So I got a personal message that I'm not able to join. It's like half an hour back. So I couldn't check the mobile in between. Sorry about that. If that person has joined now. Or you share with him or her. It's great, right? And yeah. So yeah. Any answers of the correlation? So how we go about it is we draw charts. We have so one variable, say let us call it x. One of the variables, let us call it x. Say advertisement is x, x bar, just x. And sales is one. So we write the numbers here, all the numbers we will note down here, all the 10 numbers. Then we will calculate the means here at the end, y bar and x bar. We will calculate at the bottom. Then we will have one column, xi minus x bar. So here for each xi, we will calculate this xi minus x bar. So we will have these. Okay. Then we will have another column, yi minus y bar. We will have these data. So each of these y minus the y bar, the mean of that data. So we will have those variables. Then xi minus x bar multiplied by y minus y bar. Essentially, multiplication of these two numbers for each pair. So we will have like this. And two more columns will be beneficial. That is square of these. Xi minus x bar whole square. Sorry. Okay, it will let us not waste time. So these are different columns. These are different columns. So there's required 10, 10 in this case. There are 10 data points. And in this case, the rest of the formula can easily apply if we have all these. It is easily done. So we'll do that in the next session. I think time is over. Okay. Yeah, x bar 650, y bar 660. We will check that. And then and that's they can also share. We will do that step by step. Then one more problem. If you require more preparation. All right. Thank you very much. Thank you for joining. Sorry for the confusion. I think there was some confusion today regarding classes. We'll meet again soon. Yeah. Okay. Hello. We will log off now then. Right.
Okay, sir. Bye.